Welcome to Cranky Calculus, where we are here to take the edge off, and let's go ahead and learn about some limit laws and some algebraic limits. So we have a bunch of limit laws there to the left. I got all this stuff out of a textbook by Steve Kokoska. That's where all those limit laws come into play. Pretty much limit law, number one just says if you add two limits or subtract two limits, you can separate them. Number two is the constant principle, where you can pull out a constant in front of the limit. 3 is the multiplication limit. 4 is the division one. 4 is a little tricky though. We just got to make sure that our denominator does not equal 0. Otherwise, it will be a DNE, does not exist problem. 5 is the power one. We can take the power on the function and put the entire limit to the power. 6 is just the limit of a constant is a constant. And 7 is really our direct plug-in, which we're going to be getting to here very shortly. So let's go ahead and get started on these notes here. So use the limit laws to find the limit as x approaches 4 of x squared minus 5x plus 7. So the only limit laws I see here really are just the first one. So whenever it says use limit laws, all that means is show at least one step. So that is going to be limit as x approaches 4 of x squared minus the limit as x approaches 4 of 5x. So see how I'm separating everything here? Limit as x approaches 4 of 7. So what I'm going to do now is I can do a direct plug-in, and I can get 4 squared minus 20 here because it's 5 times 4 plus 7. So I'm going to get 16 minus 20. Plus 7, I'm going to say that is a positive 3 as our answer right there. So we can do a direct plug-in to limits if the function is continuous, and we'll kind of get into that, what the heck that even means. If the limit of the denominator is 0 and the limit of the numerator is not, then the limit does not exist, but we will investigate whether the limit is going to be positive infinity or negative infinity, and we're going to get into that here in just a bit. We do have a couple of limit ratios coming up here. So what we are going to do is we are going to find these limits, and if the limit is ever of the form 0 over 0, we need to do something. What the heck does that mean? Well, factoring or multiply by the conjugate. We need to rewrite the ratio a bit so that we can find where the whole is, cancel out the whole, and rewrite the function. So on this first one right here, we have the limit as x approaches 3. Top is 3x squared minus 5x minus 12, all over x squared minus 9. If you do a direct plug-in of 3, I'm going to say you get 15 here in the middle. You get 27 minus 15 minus 12. That is going to give me 0 over 0. So I don't write equals 0 over 0. What I'm going to do here is I will factor this. So I'm going to get the limit as x approaches 3. And the top, I hope, does factor nicely. So I'm going to do, I call this the double bubble method. So it's going to be 3x, and x has to be the front one. I'm going to say this is probably 4 and 3, just by doing some guessing and checking here, because it gives me 12, outside gives me 9, inside gives me 5. Perfect. So how about a minus 9 plus 4x? So that will factor right there. So I'm going to get x plus 3, x minus 3 on the bottom. When I do this, my x minus 3's do cancel out, which is really nice and convenient, so I can rewrite this limit. And you have to keep writing limit, by the way. Don't be lazy and just drop the limit. We have to keep the limit until all of our variables are substituted in for. So we're at the point right now where I can substitute in. I can do 3 times 3 plus 4 on the top, all over 3 plus 3 on the bottom, and that's going to give me 13 over 6. If I ever make any mistakes, please comment below. Usually my mistakes are not conceptual. They're going to be algebraic mistakes in terms of simplifying. I'm not really good at that. Not my forte, but you know what? That's okay. Nobody's judging. Let's hope not. So with this one right here, with this next limit, we have this square root. And what's going to happen here is plug in a 7. It looks like I'm going to get 0 on top and 0 on the bottom. So I'm going to multiply by this conjugate. I'm actually going to make the writing a little bit smaller. So the conjugate for this top one right here is going to be x minus 5 plus root 2. I'm going to do this at top and bottom. And so what's going to end up happening here is I can rewrite this limit as x approaches 7. When I multiply across on the top, because they're conjugates, everything does cancel super nicely. I'm going to get x minus 5 minus 2. On the bottom here, I will quickly factor out that 2. I'm going to leave it as 2 x minus 7 and then times my conjugate. I'm not going to distribute anything like that because it's going to make this even uglier than it already is. So I get here on the top, I do get x minus 7, so I can actually just real quickly rewrite this top part as x minus 7. Because of that, I will be able to cancel these out, and I'm left with the limit as x approaches 7. The top is 1 over 2 times square root of x minus 5 plus root 2. I can now cleanly plug this in. When I do plug in a 7, I'm going to get 1 over 2 times, I get root 2 plus root 2, so it's going to be 2 root 2's. So, forgot to pay my electric bill. Hold on 1 second, let me pay that bill. I'm still cooking here. Finish that problem, you're going to get 1 over 4 root 2. Let me pay that bill. All you got to do is just wave your arms and electricity comes back on. All right, so those are the 2 big ways that we can go ahead and quote-unquote do something. Let's talk about piecewise functions here. Go away, colors. There we go. So we have a piecewise function here, and what we're going to do is we're going to identify each piece here. So the top one is going to be sine of pi x. That's when x is less than 1. Between 1 and 3, we're going to have x squared minus x. And on the bottom piece there, when x is greater than 3, we're going to have 1 over x minus 3. So what we're going to do here is we're going to identify each piece on these limits. So for this first one right here, in order to identify limit as f of x approaches 1, I'm going to look at the limit as x approaches 1 from the left of f of x. So for this problem, as you approach 1 to the left, that's actually going to be the top piece here because we have sine of pi x is left of 1. So actually, I'm not going to write down that f of x. I'm actually going to plug in sine of pi x. And actually, I can do a direct plug-in at this point, and I can just plug in a 1. And I'm going to get sine of pi. Anybody know what sine of pi is? Hopefully you know that. That is going to be 0. We're going to do the limit as x approaches 1 to the right of f of x. And when I do that, that's actually going to be the middle piece because that's just, since the middle piece has the boundaries between 1 and 3, 1 to the right is just between 1 and 3. So it's going to be x squared minus x. If I do a direct plug-in for 1, I'm going to get 1 squared minus 1, which is 0. These do match. Because these do match, this does now equal that same value, which is 0. So we can find the limit as x approaches 1. Let's come on over here, the limit as x approaches 3. So I'm going to look at the limit, because it's, again, a piecewise function. Look at each piece. So 3 to the left of f of x is going to be represented by can be represented by that middle piece there, which is going to be x squared minus x. It's not a ratio, I can just plug in. I'm actually going to get 3 squared minus 3, which is 6. And here comes the fun one. This is going to get us a lot of information out about how to do some of this. Some of this heavy-duty math here. So if we don't know what a rational function looks like, that's going to be kind of tough for us, but I'll see what we can do here. If I were to plug in a 3, I'm going to get a number over 0. And as I did in the previous slide here, it says that if the limit of the denominator is 0 and the limit of the numerator is not, we have to investigate and we have to figure out if the limit is infinity or negative infinity. If possible, or maybe if it's one-sided, it will be negative infinity or positive infinity. if it is not one-sided, it's possible to get different infinite values on each side. So what I'm going to do for this, I'm going to look at 1 over x minus 3. I do this doing a sign chart. That's just me. So I'm going to do my sign chart on over here. Here's f of x. And on my sign chart, I have a vertical asymptote at 3. Okay, that line just means a vertical asymptote. And so I'm going to look at values to the right of it. And it's very obvious that the right end behavior gives us positive values. You can do that by either plugging in like a 4 or a 5, which will give us positive values. Or we just know that since the x minus 3 term is positive and the 1 is positive, we're going to get everything as positive. Now, at the x minus 3, since there's a power 1 right there, we are going to change signs because the graph is going to not necessarily go through the x-axis, but it is going to change signs because we have a power 1. Every single factor we have that has an odd power, that means we will change signs. This is for polynomials, this is for rational functions. If we have an even power, like x minus 3 squared, we're going to keep the signs. This is an odd power, so we do change signs right here. And if I'm looking at 3 to the right, I'm going to positive, so this is going to give me a positive infinity, because any number over 0 for a one-sided limit is going to be negative or positive infinity. Since I have positive values to the right of 3, it's going to give me a positive infinity. Now, since the limit as 3 to the left and 3 to the right do not equal, this right here is a solution of does not exist. Though it does not exist, I write DNE for does not exist, and I'm going to just real quickly wrap this up nicely, and that is because the limit as x approaches 3 to the left of this f of x does not equal the limit as x approaches 3 to the right. And that is going to wrap up this video. If you want to see more videos like this, you need to like and subscribe and ring that bell.